Let's get a sketch of the cylindrical tin down. So here we go. We know the radius is r. We've given the volume. Okay, somehow the height is going to be involved. So the first thing I'm going to do, I've not even really read part A, but I'm just going to write down an equation. The volume of a cylinder is pi r squared h. It's the area of the cross-section times by the length of this cross-section. So therefore I can write 16,000 pi is equal to pi r squared h. I can cancel the pi's out. Right, let's focus now on actually what we're being asked to do. So we're asked to show that the surface area is given by this. Now note, it's in terms of r, whereas I've got h up here. But let's write down the surface area so far, A. Well, it's going to be the top circle, pi r squared, plus the bottom circle, which is also pi r squared. So I can just write 2 pi r squared, plus the length of the curve, sorry, the area of the curved surface area. And this is 2 pi r h. The reason being is that when you open this out, it will become a rectangle with height h, and the length is going to be the perimeter of the circle, which is pi d or 2 pi r. So that's where this came from. So we're well on our way now. It's just that I don't want h in my answer, but we can see now I've got this up here that I can deal with. I can make h the subject, so it's going to be 16,000 divided by r squared. Okay, I'm nearly there. So it's going to be 2 pi r squared plus 2 pi r times 16,000 over r squared. This r is going to cancel with one of those because I'm timesing by r and dividing by r. And then the 2 times 16,000 is going to give 32,000. Still got my pi in there, but it's going to become r to the minus 1. I feel like that's enough. This is a show that question, so you got to show enough work in, but I feel that's definitely enough. We're then asked to calculate the minimum surface area and justify that it is a minimum. Okay, this is going to involve differentiation. We've got some sort of function. It's like an r, it's r squared, but it's got an r to the minus 1. Not entirely sure what it's going to look like, but at some point there's going to be a minimum. And therefore, I need to find dA by dr, which is the instantaneous gradient, and then set that equal to 0. So differentiating this, I'm going to get 4 pi r. And over here, I'm going to get minus 32,000 pi r to the minus 2. Of course, I've just used the fact that d by dx of x to the n is nx to the n minus 1. The constant just passed through, so you could put a k in front of each if you wanted. So times by the 2, and then lower the power, 4 pi r. Here, times by the minus 1, and lower the power to minus 2. I'm not going to go into any more detail on that. That's year 1 differentiation. But look back at it if you're not confident with that. And then this is going to equal 0 for stationary points. When I did this question myself, I actually started by saying to find the minimum surface area, locate stationary points of A, but I'm sort of implying that as I do it here. Right, let's write it out again. 4 pi r minus 32,000 pi all over r squared equals 0. I can cancel out pi, and I can even divide through by 4 to be fair. So if I divide through by 2, I'll do this bit by bit. I'm going to get 16,000. And then divide through by 2 again, so that's going to leave 1. I'm going to get 8,000. I could have done that all in one go, but oh well. Now I'm going to times through by r squared, so r cubed minus 8,000 is 0, so r cubed equals 8,000. And therefore r is equal to 20. Put that in your calculator, you might be able to recognize that it is actually 8 times 1,000, and you can just cube root both, but to be fair, maybe just best to be safe and put it in your calculator. So r is 20. Now it's asked us for the minimum total surface area. So I found out the value of r that will give the minimum total surface area, and therefore I need to put it back in. Min area A is going to be 2 pi times 20 squared plus 32,000 pi over 20. All right, I'm definitely using my calculator for this, just because I don't want to make a mistake or anything. So 2,400 pi. Technically centimeters squared, that's not essential. You could, of course, write it to three significant figures, but there's no harm in leaving it exact in this sort of pure situation. Maybe I will just write it 7540. Okay, because like in a meaningful context, you don't want it in terms of pi. And then justify it's a minimum. Okay, need to do that. So for this, the first approach is to try the second derivative. That fails because it's equal to 0. Then you have to do a different approach. I'm not going to talk about that here. I think I'm just going to focus on the second derivative. It's going to work. So I'm going to get 4 pi plus, and then I times by the minus 2. So I'm going to get plus 64,000 pi r to the minus 3, which I can actually just write as divided by r cubed. So when r equals 20, I mean, you can immediately look at this and see it's going to be positive. So arguably you could just say, hey, this is going to be greater than 0. But I suppose we're justifying, I don't, definitely don't want to lose any marks for rushing, even though it's clear we're adding two positives together. So let's figure it out. 4 pi. Okay, 12 pi. This is greater than 0, which implies a minimum.